I want you to start by thinking about this filter. Hey, pipe down. V in, R, C, V out. Let's describe what we already know about this. It's a low pass filter, all right? Even I know that. So we're using this. We use this circuit a lot because it's sort of like your easiest entry-level filter. But all the properties that we derive related to this filter apply to all other filters. Okay. So let's just discuss briefly what we know about this. We know it's. I believe we've calculated its step response. All right, and its step response should be V out as a function of time equals 1 minus e to the minus t over RC. Okay, which if you were to plot it, looks like that. Okay? What is today's date? 22nd. Deuce deuce. Almost November. How did that happen? Okay, so that's the step response. That's the capacitor charging. We also know that the transfer function is what? Let's see if we can remember it. H of omega equals 1 over j omega RC plus 1. Okay? Now, remember what the transfer function tells us. The interpretation of the transfer function is that V out as a function of frequency is equal to H of omega times V in as a function of frequency. So in other words, if you know the transfer function, it's a tool for getting the output signal. All right? This is all stuff we learned. We also learned that if you take the magnitude of H of omega, remember H of omega is a complex function. Okay? This always is a complex function. And if you take its magnitude, that tells you, like that will let you see what kind of filter. Right? If you take its transfer function and plot the magnitude versus frequency, that's what will make it so that you can see that, oh, this is a low pass filter, for example. Okay? This is what H of omega might look like. Okay? So far, this is all stuff we've seen. Now, today, we add a new wrinkle, a new element to this. All right? So, here's how this game is going to be played. I want to calculate the impulse response. I'll tell you why later. So far you know what the step response is, right? The step response is how the circuit responds to a step. I want to know the impulse response. The impulse response is what comes out when your input is an impulse. Right? So this is essentially saying what is V out of t when V in of t equals delta. Delta is, that's our shorthand for impulse. Okay. So, first thing I want to do is get this impulse response. And like I said, I'll tell you why in a minute, but it's all related. And what I want to do is to get that response with the least amount of calculus possible. I don't want to solve a differential equation if I don't have to. The good news is that most of the information I need is already on the board. So here's the standard trick for solving for the impulse response. So here is a step. Okay, is that not a step? Okay. Here is and impulse. I want somebody to dig deep and guess for me. I'm not talking about step response or impulse response. I'm just showing you a step and an impulse. Is there a relationship between a step and an impulse? Yes. What is that relationship?
Time differentiation.
Time differentiation. How do you mean?
If you time differentiate the step function, you get the impulse.
If I take d dt of the step, I get the impulse. Is that correct? Let's see here. Okay, so let's take the step. For t less than 0, if I take its derivative, I get 0. That's consistent. If I take t greater than 0 of the step and take its derivative, I get 0. So that's consistent. What if I take the derivative at t equals 0? I get, remember this is like a line whose so steep that its slope is infinity, but only at t equals 0. So it is true. If you take a step and take its derivative, you get an impulse. Conversely, if you take an impulse and integrate it, you get the step. Actually, I'm going to take out the dt because it can be impulse with respect to anything. You get the step. Okay? Now, owing to the wonders of modern calculus, tell me. Oh, the board works perfectly today. Nice. Okay, so tell me, if the derivative of the step is the impulse, what do you think is the derivative of the step response?
The impulse response?
Yeah. If you take the derivative of the step response, then you get the impulse response, which is kind of cool, right? In essence, what I'm saying is, like, let's say this is your system. And suppose we were putting in a step, and what came out was the step response. If our system is linear time invariant, you've heard that term before, LTI?
What is the C stand for LTIC?
Linear time invariant. I don't know what the C stands for.
I always see LTIC.
I have not seen that. I'll find out for you. LTI, so LTI, linear time invariant. So basically, linear time invariant means like if you double the input, you double the output. If you shift the input by 1 second, you shift the output by 1 second. But it also means that if you take the derivative of the input, you take the derivative of the output. Doesn't it mean that? Right? If you double the input, you double the output. If you take the derivative of the input, then equivalently you take the derivative of the output. You don't even need to do all the math that goes on the inside. And conveniently enough, I know this step response. Conveniently, I already wrote it on the board. How about that? So, what is my impulse response, h of t? H of t, so this is little h of t. That's one of these like magical, like that's like a reserved word, right? We're always going to agree on that. Okay, so h of t will always be the impulse response. Okay, so how can I get my impulse response? Take the derivative of the step response. So that's going to be d dt of 1 minus e to the minus t over RC. Hey, that's not even that ugly, right? Who can help me out here? Who took calculus? All right, the derivative of the 1 is a 0. So now I've got to take the derivative of the exponent. Let's see, I know that the stuff in the exponent comes out. The minuses cancel. So I'm left with 1 over RC e to the minus t over RC. Okay, and that's only for positive time. Right? Because for negative time, it's 0. What does that look?
The switch is still not turned yet. Right?
Well, the impulse was 0 for negative time. So if there was negative, there was no input, there was no output. Okay, then at t equals 0, you kick the system with an impulse, and then this is the system's response to that impulse that started at t equals 0. So yeah, it's only for positive time. What's that look like if I were to plot that? Not the same thing. It's going to have a different shape.
It's going to be a decay.
It's going to start at 1 over RC. I agree with that. Because if you let t equal 0, you get e to the 0 is 1. You're left with 1 over RC. And then it decays away. Okay. That's your impulse response. Then that sort of makes sense. If you kick the system with an impulse, essentially the cap charges instantaneously. And then there's no more input after that instantaneous impulse. So then the cap just, the voltage on the cap just dissipates out through the resistor. That's what you're seeing here. Okay, so there's your impulse response. Nice. All right, pat yourselves on the back. Okay, you ready for the next step? Now, for reasons that will become apparent shortly, I'm a big fan of not telling you my reasons till the end. Okay? But hopefully all the pieces to the puzzle will fit soon. All right, we're only 15 minutes in. We're good to go. Now what we're going to do is we're going to take the Fourier transform of the impulse response of the system. That's right. The Fourier transform of the impulse response of the system. So, I'm taking my system, I'm kicking it with an impulse. I've calculated what the impulse response is. I now wish to know what are the frequency characteristics of my impulse response. All right? Let's find out. So let's actually just apply the formula for the Fourier transform, right? Because that's really our only play at this point.
Quick question.
Yes, sir.
When we found h of omega, was that the Fourier transform of v of t?
So what I did to find h of omega is that I calculated this by taking the Fourier transform of the differential equation.
That's the system.
Right. That's how I got that. I took the differential equation, which describes the system, and I took its Fourier transform to find out how that operates in a frequency perspective, and that's how I came up with that equation.
So that's the Fourier transform of the system, not the output.
Right. This does not, you can't know the output unless you know the input. This just tells you how to take your input and calculate your output for that particular system. Okay, this doesn't tell you the output, it just tells you how the system responds to an input. Good. Awesome questions. Okay, so let's apply I want to apply the definition of Fourier transform. Yes, sir?
Yeah, before we go there, back to the impulse response. So if the vertical axis is 1 over RC, the horizontal will be the time that it took to discharge or charge. That will be the time constant there.
Well, this is time.
This in time.
Yeah, and it will take, as with any decaying exponential, it will take roughly 5 time constants to decay. But we're not really too concerned with that. Roughly like this would be 5 RC, if that makes you feel better. But that's not really, that's just an arbitrary point to plot. Okay? All right, so I'm going to apply the definition of the Fourier transform. So the Fourier transform says integrate over all time, whatever your function is, e to the minus j omega t dt. Is that right? That is what we do. Okay, good. So in this case, my function that I'm taking the Fourier transform of is 1 over RC e to the minus t over RC. So that's my function that I'm taking the Fourier transform of. All right. So I'm taking that and multiplying it by e to the minus j omega t. And I'm integrating it from what to what? All time. Really? All time? Starting at 0. Because this function only applies starting at time 0. Right? Before that, for time less than 0, the function that I have is 0. And if I integrate it, I get nothing. So we're not even going to integrate it. So I'm integrating starting at time 0 and ending at infinity. Okay? And again, the reason I don't have to integrate the negative times is that my function equals 0 for those times. So integrating them doesn't give me anything. Okay. It's time to put our calculus hats on. Okay. So somebody help me with this mess?
Multiply the RC can come out.
Right. Multiply. So we can take out the RC because that's a constant, and then we can combine the exponents, right? So let's see. That's 1 over RC integral from 0 to infinity of e to the minus, let's see if I can get this right on the first try, 1 over RC plus j omega t dt. So far so good? Tell me if I'm lying. You agree? I agree too. All right. So far so good. All right, next step. Well, I do need to integrate, but I want to be careful. We know when I integrate e to the at that I'm going to get 1 over a e to the at. And then this is my a. So it's going to be 1 over that nonsense. It's not really pretty. Why don't we start by combining this into a single, like combine this exponent into a single fraction just so it's a little neater to integrate. So like why don't I just basically make a common denominator and add? I don't strictly have to do that. That's just like a stylistic thing to kind of, because I'm anticipating not having to write an ugly fraction that I don't want to write. So over here on my scratch paper, if I have 1 over RC plus j omega and I want to combine that into a fraction, what's that going to be? 1 plus j omega RC over RC. Okay, so that's just making a common denominator and adding those fractions together. Okay, so now I'm ready to integrate. So I've got my 1 over RC. That's this 1 over RC. And now I've got minus 1 over a. So that's going to be minus RC over 1 plus j omega RC. So remember, it's 1 over my exponent. So I flip my exponent. And there's also a minus that needs to come out. So there's your minus. And then it's e to the minus, I'm just going to put a right now so I don't have to rewrite all that. E to the minus at from 0 to infinity. And we can all agree that this a is just shorthand for this, because I really don't feel like writing that again. And as it turns out, it's not going to be all that necessary anyway. You with me? Hey, did you notice how these RCs cancel? Good. So the RCs cancel. That's pretty good. So now I got to substitute in for t. So I've got e to the minus a infinity. It's going to be 0, right? E to the minus infinity is always 0. So I've got 0 minus, and then then I sub in 0, so it's e to the minus 0, which is 1. Oh man, I am liking that. So 0 minus 1 is negative 1. That minus cancels this minus. And what am I left with? 1 over 1 plus j omega RC. Hey, have we seen that before? Yes. So what happened here? Okay. Believe it or not, I actually care very little about the math that we just did. But I care incredibly about the concept of what we just did. And I want to make sure that we tease that out, because there's like 4 pieces of this puzzle that we have to kind of wedge together. Sorry, the impulse response and the
step response have the same transfer function.
not quite. We never took the Fourier transform with the step response. No, we
did not. You're right.
the Fourier the differential equation. We took the Fourier transform with the differential equation. Yes.
If we take the Fourier transform of the impulse response, we get the transfer function.
Yes, that will always be true. But I want to think about why that's true. Yes.
It's like your key input is going to be 1 in the frequency domain.
Yep. Okay, so let's tease this apart. So the input to in this experiment, my input, so here's my system, okay? My input was an impulse. From a frequency perspective, what does an impulse look like with respect to frequency? We learned this, right? And I told you it was important, and I told you to write it down on a piece of paper because we were going to need it. All frequencies. It's constant across frequencies. If you take the Fourier transform of an impulse, you get a constant. I'm just going to draw the positive frequencies for now, but you know it also exists for the negative frequencies. It's a constant across frequencies. So when I kick my system with an impulse, what I'm really doing is presenting to my system in one go all frequencies, right? I mean, if I gave you this system and I said, please figure out if this is a low-pass filter or a high-pass filter. The circuits 2 approach is to say, okay, first I'm going to generate a cosine at 1 hertz. Then I'm going to generate a cosine at 10 hertz, and 100, and 1,000, and 10,000. Right? And for each one of those inputs, you go and you measure the output, and you look to see how big the output is. Okay, and you say, well, the input was 1 volt peak to peak. The output was 1 volt peak to peak. That frequency got passed. Then you try another frequency, and another, and another, and another, and you figure out which frequencies are passed and which frequencies are rejected. Now what you're doing, when you present this input, this impulse, instead of doing 1 cosine at a time, insanely, you're doing all cosines at the same time. I'm telling you, it's pretty cool, right? You're putting in all frequencies at once. Let that sink in. That's a pretty profound statement, right? In one go, you're testing the system's response to all frequencies. Now, the system will respond. Like you go and you hook up your oscilloscope and your system had some sort of impulse response h of t. Okay, and we were able to calculate h of t by hand. Who cares? But conceptually, if you take your system and present it with all frequencies, intuitively, the system response should look basically like either a low-pass filter or a high-pass filter or whatever kind of filter your system is. I mean, if your system was a low-pass filter and you presented it with all frequencies, then what you would expect at the output is you would see whatever frequencies you put in that were being passed are retained, and then whatever frequencies are being rejected, you get rid of. I mean, that's basically what you're doing is you're testing all the frequencies at once. So when you look at your output, what you expect to see is the system's response to each and every frequency. Okay? And as it turns out, we happen to know that we already know that that's equal to h of omega, which is the transfer function which we got by the differential equation. Okay? So, it shouldn't surprise us that the Fourier transform of the impulse response is the transfer function. Okay? Because then impulse tests all frequencies. Therefore, the impulse response must be the response to all frequencies. Okay? And what is the response to all frequencies if not the transfer function? So it all fits. And that, in this case, I've just used our little rinky-dink RC circuit to make my point. But insanely, this point always holds. No matter what linear time invariant system you show, all right, they always have this property that the relationship between the impulse response and the transfer function is just the Fourier transform. Okay? It's pretty intense. And that's what you're going to do in recitation this week. Right? In recitation this week, I give you some really ugly circuits, and I ask you to do two things. First thing I ask you to do is to calculate the transfer function, okay, using complex impedances like we talked about in class last week. So basically, every time you see a capacitor, you'll just say, oh, that's 1 over j omega c. That's like a resistor with value 1 over j omega c. And everywhere you see an inductor, you say that's like a resistor with value j omega L. And then you just use your regular old mesh and node analysis to get the transfer function. And that's fine. Then you figure out what kind of circuit it is. All right? But the fun bit is that I've also calculated, I did this, so you don't have to. I'm giving you for each of the circuits the impulse response of the circuit. And then I say, here's the impulse response. Take its Fourier transform and verify that it comes out to the same transfer function that you got for analyzing the circuit by hand. All the pieces of the puzzle should fit together. Crazy, right? Okay, so this is conceptually, this is like pretty high end, right? There's a lot of pieces to this. So, what I want to do is just to kind of, to help you piece this together and to set up the next lecture, is I want to revisit something that we looked at on MATLAB before. I'm just going to kind of sketch what we saw in MATLAB. Do you remember when we took the rectangular pulse and we filtered it? Right, we took the rectangular pulse, we did a low-pass filter. We did that, right? Yeah. And we got
Like a shark.
Yeah. Right. So it kind of, after we filtered it, it looked a little bit like this, and then a little bit like this, and we talked about why that was. Okay. So I'm going to sort of redraw that MATLAB thing that we did. I'm going to just redraw it on the board. So here's what we did. We said, all right, suppose your input signal is, so this is the input row, and this is the time column. So this is what your input signal looks like with respect to time. Okay, and then we took its Fourier transform, did we not? Okay, so what did the Fourier transform of the input look like? Sinc function, all right. Everybody should know that. Doink, 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 doink. Doink, 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 doink. Your results may vary. Okay, and we discussed this general concept that if this gets wider, that gets skinnier and vice versa. Okay, so we called this V in with respect to frequency, and we called this V in with respect to time. Good. Then the next thing we said was we were going to low-pass filter this. So to build a, remember that's 0. Oops. So to low-pass filter this, what we said, how do we say we're going to do that? No, I don't care about how I actually executed it in MATLAB. Right. So we had a transfer function, that was a low-pass filter that looks something like that, right? That a low-pass filter? Yep. If I wanted to, I could also draw the negative frequencies. Okay, it's still a low-pass filter because these are negative frequencies. I'm basically just passing the low frequencies and rejecting the high ones. So don't be distracted by the fact that I also drew the negative frequencies. You know that's going to be a mirror image. Okay, so I did this. And then I said, aha! Well, remember we had just, at the time, we had just studied this thing, and we had determined that V out as a function of time equaled h of omega times V out as a function of frequency equal transfer function times V in as a function of frequency. So in essence, I took this plot and this plot and multiplied them. You remember that conversation? Okay, so when I did that, for the low frequencies, got passed. Okay, maybe like the second one. But then after that, my high frequencies got multiplied by pretty small multipliers. So those kind of very quickly died away. And then finally, I took I can draw the negative frequencies here too, if I'm so inclined. So you notice the difference between, like here I had high frequencies, and here those high frequency components are basically thrown away. Okay, so that's the effect of the filter. And then when I took the inverse Fourier transform of this, what happened?
We had exponential.
Yeah, exactly. I got my little shark fin looking thing. So this is V out as a function of time. Okay, and we argued that this even made sense, right? Because essentially what we were doing is we were getting rid of the high frequencies. The high frequencies are exactly the bits that you need to give definition to the high frequency edges. So if you dump those high frequencies, you should expect that your high frequency edges will be smoothed out. Okay, so the pathway that we said was, here's your input signal versus time. You take your input signal, convert it to frequency. Take that, multiply it by the transfer function to get your output signal with respect to frequency, and then take the inverse Fourier transform, and ta-da, you know what your output signal looks like. Which is cool, right? There's, like at least half the time where that kind of analysis makes sense. But you'll notice that we left one plot blank. Right? Shouldn't there be a plot that goes here? There's a plot missing. Well, now you know what goes here. What goes in this empty axis?
The impulse response.
That's the impulse response, right? I mean, essentially what's going on here is if you take the Fourier transform of the plot on the left, you get the plot on the right. Okay, so if you take the Fourier transform of your input, you get V in with respect to omega. Take Fourier transform of your output, you get V out with respect to omega. So, we've just learned, what function is it that if you take its Fourier transform, you get the transfer function? Well, it's the impulse response. So what goes here has to be the impulse response. So that's the last piece of the puzzle. Crazy! Now, turns out there's one more piece of this. It's cool and all that we know that this box has to be the impulse response. But I wonder, is there any way, like my goal is always to figure out V out with respect to time, let's say. Right now, the only method I have of getting V out with respect to time is to go all the way around and do my analysis in the frequency domain. I'm wondering, is there a way where if I know V in with respect to time, and I know the impulse response with respect to time, is there any way for me to get my answer just going in the time domain? Like, am I obligated to go through the frequency domain to get my answer?
You do convolution.
Could I multiply? What do you think? If this and this multiply, do I get that?
Well, if you use convolution theorem, you can say that you multiply them in the frequency domain, so you have to do convolution in the time to
We
beat.
don't even talk about what is. I don't even know what convolution is. I mean, yes.
We subtract the upside down figure from the front and then add the right side figure up from the back.
What?
Flip it over, put it on the front
This-
side,
wait.
subtract it. Flip it up.
This guy.
Yeah, flip it upward. Subtract it from the front part.
Does it stick out of the board?
So you're going to end up with a U shape.
That's crazy. No, not crazy bad. I mean, just like that's. I've not even thought about visualizing it that way.
Well, you take the.
I think you would be lucky if you. I mean, you might be able to. You might be able to do some sort of contortions and get it to work, but I think you'd be lucky just owing to the shape of this thing. Like, well, I mean, I could come up with any shape, right? I mean, why a rectangle? Why not? You know, what if I gave you this function? Okay, I mean, would your plan work if it was that function?
I don't know, that's a small example.
All right, that's cool. Okay, so basically, we are headed to convolution, and that's the lecture we're going to have on Friday. Oh, no, Wednesday, I beg your pardon. Okay, so there are basically two ways of skinning this cat. Okay, well, method one of getting your output is to do the frequency-based analysis, which is fine. I mean, it's not bad. It's there, it's part of it. But I'm now teaching you the other part of it, okay? Which is, instead of a frequency-based analysis, you could also get your answer using a time-based analysis. And by definition, it has to be equivalent, okay? For two reasons. One, there's only one right answer. And it doesn't matter how you get there. You should only, I mean, the pathway you get there shouldn't matter. There's only one right answer. And two, logically, it's consistent, right? I mean, we've talked about the equivalence between the transfer function and the impulse response. You know, if everything's equivalent frequency and time, there should be an equivalent method of doing your analysis in the time domain. Okay? And that's what we're going to talk about. And I have a cool method of describing how to set up that integral, which I think you're going to agree kind of makes the convolution integral make a little bit more sense. But I would just like to make the point that, you remember how like on the first day, I argued the case that looking at a signal with respect to time and looking at a signal with respect to frequency were completely identical. Like whether or not you looked at the time or the frequency representation, they were telling you the same thing, right? Well, it's exactly the same case for the transfer function or the impulse response. They're really telling you exactly the same information. If I tell you the impulse response, that's all you need to know, okay? That's enough to tell you that we're dealing with a low-pass filter circuit. It's enough to tell you what the cutoff frequency of the low-pass filter circuit, right? This is a complete representation of the system. Likewise, this is a complete representation of the system. Okay, this also tells you everything you need to know about the system. Okay? If you have this, you can get the impulse response. You can get the step response. You can get everything. Okay? The other thing that you could have that's completely equivalent is the differential equation. Right? I mean, so all of those are equivalent representations of the same system. If I gave you the differential equation, right, my argument from day one was that's a complete representation of what this circuit does. Well, it's true. If you took the differential equation, took its Fourier transform, you'd have that. There you go. Once you have that, you have everything.
So is the differential equation just a representation of the impulse response?
Yeah, yeah, you can actually solve the differential equation for the impulse response, but it's just ugly mathematically. So instead what we did was we solved the differential equation for the step response, right? I mean, that's how we actually got the step response, is we solved the differential equation and then differentiated it. That was like our backdoor approach, that we didn't have to deal with some of the more unseemly math that goes into a impulse response through a differential equation. But it's all there, right? It's all these like pieces of the puzzle that fit together. And really, like conceptually, I just want you to get that concept that an impulse contains all frequencies. So if you take all frequencies and present them to a system in the form of an impulse, you'll get the impulse response, which is in one fell swoop, the system's response to all frequencies. It's insane, and it totally works. Okay?
Can you do that for filter 2 to see how it will respond?
Totally. Now, I will caution you this as I get your quiz out. You cannot, there's no button on your function generator that says impulse. It's very hard to create an impulse in a function generator. But it is easy to create a step or a square wave. And that's equivalent, right? Because if you look at the system's response to a step, you could just differentiate it, and then you would know the system's response to that impulse that you can't create. So it works out nicely. All right, have some